So in last lecture we have studied triangle law of vector addition. In this lecture we will study parallelogram law of vector addition. So just consider two vectors OA and OB as the two adjacent sides of a parallelogram, then their resultant will be a diagonal of this parallelogram. If we extend these two vectors and make a parallelogram, then the diagonal of these two will be the resultant vector of these two given vectors. So what are the given vectors? OA and OB. So resultant is nothing but O is OC. We represent it with R bar and this given vector P bar and Q bar. So these two adjacent sides of a parallelogram, if we take these two and we want to find the resultant vector, we will get the diagonal as a resultant vector. What the parallelogram law of vector addition says, it says if you represent two vectors in magnitude and direction by the two adjacent sides of a parallelogram, then the resultant will be this diagonal. It originates from the O, that is common point of these two vectors. Now let's calculate the resultant or the magnitude of resultant R bar. Now for this we need to extend this OA bar up to D and the perpendicular from C to D. Okay, so here it is making 90 degrees angle. Now this angle we know theta, as these two vectors are parallel, this angle also will be theta, and this phi is angle made by this R bar to this OA bar. Okay, so angle BOD is equal to CAD, that is theta, and AC bar is equal to Q bar. Here this is Q bar, OB is a Q bar, so AC, as they are parallel, we know this is also Q bar. Now consider this right angle triangle CAD. Here we can see CD by AC, that is nothing but a sine theta. We know opposite side by hypotenuse. So we will get the value of CD as AC sine theta or Q sine theta. We can see here this AC is nothing but Q. Now similarly AD by AC, AD by this hypotenuse, adjacent side by hypotenuse is a cos theta. So AD is AC cos theta is equal to Q cos theta, because AC is again Q. So we got these two relations. Now consider the right angle triangle COD. Okay, here OC square, that is resultant R bar, OC square is equal to, we know by the Pythagoras theorem, OD square plus CD square. So OD square plus CD square. Okay, we know OC square is equal to OD square plus CD square. Now we know OD has two parts, OA plus AD. So we just put these two values, OA plus AD whole square plus CD square. Now we know this is a plus B whole square. We can expand this bracket, A square plus 2AB into plus B square. So we just expanded this, OA square plus 2 times A and B, that is OA AD plus AD square B square, so plus CD square. Now we know in right angle triangle CAD, that is we have the relation CD is equal to Q sin theta, AD is equal to Q sin theta. Here you can see if you make square of these two and add, that means this AC square term will get common outside, and sin square theta, this sin square theta cos square theta will be 1. So we will get AC square from this CD square plus AD square. So we just take this AD square plus CD square is equal to AC square in our term here, AD square plus CD square. So just put this value, that is AC square, okay, OA square as it is, 2OA AD as it is, and this, for this we take the AC square here. So OC square, we know OC is R bar, OA is P bar, AC is here Q bar, okay, and 2. So AD, we know AD is a Q cos theta. So just put this value, we got the resultant R square. We need value of R, that is magnitude of R, so under root this whole term. So this is a magnitude of a resultant of two vectors by parallelogram law of vector addition. Now we will find the angle, that is phi, made by the resultant to the OA. Okay, so this phi we are going to find the value of phi. For this we need these two sides CD. Consider this triangle COD. So we know it is a right angle triangle. CD by OD is nothing but sin phi by cos phi. So from this we know tan phi is nothing but sin by cos. So sin phi is CD, cos phi is OD. So we have the value for OD, OA plus AD. Then CD's value, OA plus AD's value, we just put these values and get phi as a tan inverse of this whole term. This is the value for phi, that is angle made by resultant with respect to a vector. So let's find some values for particular angles like 90, 0 degree and 180 degree. So we just take these two values phi and r. So this is resultant, we know. So put the value of theta in these two equations. For firstly in this equation of resultant. Okay, so when theta is 90, cos is 0, we know. So this term gets cancelled and we get r is equal to p square plus q square. In this situation or in this equation, we just put the value of theta as 90. Sin 90 is 1, so the numerator is there. So cos 90 is 0, so this term gets cancelled and only p remains. So that is phi is equal to tan inverse of q by p. You can check next values for theta is equal to 0 degree and theta is equal to 180 degree. So consider this diagram. Here we have taken two vectors p bar, q bar. Let's consider this negative of this vector, that is minus q bar, along this direction. We know the negative of this is opposite to the original. Okay, so if we want to add, that is p bar plus q bar, we know by the law of parallelogram of vector addition, the diagonal of this parallelogram will represent the resultant r bar, which is equal to p bar. So we are representing this resultant by the diagonal of this parallelogram. So resultant is p bar plus q bar. Now we know this is a negative or a opposite negative vector or opposite vector of this q bar. It is equal in magnitude but in a negative direction or opposite direction from this q bar. So if we want to add these two, so we just put this diagonal using common point of these two as origin, and we write here resultant. Let's say this is r bar, so let's say r bar dash is equal to this diagonal p bar minus q bar. So this is addition, this is subtraction. Now after these two laws, let's consider a property that is a commutative law for vectors. We know, just consider these two vectors as a bar and b bar. So these are a bar and b bar. We know by law of triangle law of vector addition, if these two represent two sides of a triangle, then the third side represents a resultant r bar. So if you take the cyclic order, then the direction of resultant is opposite to that cyclic order. So there will be the direction of this vector, that is terminus, and there is a origin. Now this is what this is r bar is equal to a bar plus b bar. Now consider another case here. To this one parallel, we draw this b bar. Okay, for this one again another one parallel, consider it here. Okay, so that is a bar. Now if we want to add these two, b bar and a bar, so add b bar plus a bar. So in the cyclic order we can see, so this is a cyclic order, so resultant will be this one and the resultant's direction will be opposite to the cyclic order. So this is cyclic order, opposite to this direction there will be the direction of resultant. So we know this is a bar plus b bar, which is equal to r bar. So this is a commutative law of vector addition. If you take a bar plus b bar or b bar plus a bar, we will get a resultant r bar. So this is a commutative law of vector addition. Now we will study associative law of vector addition. Here, if we change the order of addition in this equation, we can see a bar plus b bar plus c bar, okay, is equal to a bar plus b bar plus c bar. So in associative law, we know if we change the order of the addition, then that is if we add b bar plus c bar in a bar, or if we add firstly the a bar plus b bar and then add into the c bar, then the resultant is same. So by diagram we can show, consider this a bar, this b bar and this c bar. Now we know a bar, b bar, c bar. So for this b bar and c bar, that will be the resultant we know by triangle law of vector addition, that is b bar plus c bar. For this a and b, this one will be a bar plus b bar. Now consider this first term here, b bar plus c bar, that means this vector, plus a bar, that is this one. We know their resultant is this one, so that is r bar. Now consider the second case, a bar plus b bar, that is this vector, and plus c bar, that is this vector. So we know using triangle law of vector addition, this is again r bar. We will see if vectors are given in their rectangular components, as we know I bar, 5i bar, 3j bar plus, let's take. So these are the rectangular components of b bar, these are the rectangular components of a bar. Then simply if you want to add these two vectors, we just simply add these two. Just write, I will write this one step of vector addition. So we can just add the individual components of I, that is 5 plus 2, here 5, here 2, outside the bracket I, plus the components of j, that is 3 minus 2, plus components of k. So 5 plus 2, 7i, plus 3 minus 2, that is 1j bar, plus it is 1k bar. So this is a resultant r bar. Now we know magnitude of r bar as a magnitude of a bar plus b bar, that is under root 7 square, that is this part, this one, this one. So we know this, we have seen this, so that will be 51 under root 51. Now for unit vector, we know the vector divided by its magnitude. So the vector 7i bar j bar plus k bar by under root 51. So that's simply 7 by under root 51 I bar plus 7, that is 1, j bar by under root 51 plus k bar by under root 50. Let's study the scalar product of two vectors, scalar or dot product. We know this. So consider these two vectors, a bar and b bar, making an angle theta with each other. Okay, so the scalar product or dot product of these two is given as a bar dot b bar is equal to, represented by this dot, okay, is equal to magnitudes, the product of their magnitude into cos theta, that is cos of angle between them. Here we can see this quantity a bar dot b bar is a scalar one, because there is no vector quantity. This is magnitude, and this is a angle which is a scalar quantity. So the scalar or dot product is a scalar quantity. See characteristics of scalar or dot product. Here first one, scalar product is commutative. So we can see the dot product of a bar dot b bar is same as or equal to b bar dot a bar. That means if we change the order of a dot product or scalar product, the value does not changes. So here we can see a bar dot b bar is equal to ab cos theta. We know this, but b bar dot a bar is also ba cos theta. That is their magnitude, product of their magnitudes. So b dot a or a dot b, they are same. So this is again ab cos theta. So we can prove this. Now the third case here, if a bar and b bar are parallel, that means their angle will be 0. Okay, we know this. So in this our formula, a bar dot b bar, sorry, it is not bar here, ab cos theta, there will be theta will be 0, that is cos 0 is 1. So just put this value, we get the magnitude a dot b. Now if we consider a bar is equal to b bar, then the product will be, that means if we take a scalar product of a vector with itself, then the resultant will be square of its magnitude. Now if these two vectors are perpendicular to each other, then the angle will be 90. We know this. So cos 90 will be 0 and the resultant will be 0. So if the vectors are parallel, their resultant will be their magnitudes only, because the angle will be 0. If they are if both the vectors are same, that is a scalar product with itself, the vector itself will be square of its magnitude. And if the both vectors are perpendicular to each other, then cos 90 will be 0 and we will get a 0. Now consider using these third characteristics of vectors, if they are parallel, or here in this special case we have taken individual vector, it's a scalar product with itself, that is the resultant will be square of its magnitude. Now we will apply this for a unit vectors along x-axis, y-axis and z-axis. So for I dot I, that will be its square of its magnitude, that is 1, because unit vector's magnitude is 1. So this 1 into 1, that will be again 1. So j dot j, k dot k, same, the answer is 1. Now use this fourth characteristics. So here if they are perpendicular, the both vectors are perpendicular to each other, then the resultant will be 0, that is scalar product is 0. That is I bar dot j bar is equal to I bar dot k bar is equal to k bar dot I bar. Similarly you can write all of these will be equal to 0. So if you take these two vectors as different vectors, because we know in the third 3 dimensions, if we take this x, this y and this z, then there will be I, j and k. They are mutually perpendicular, so I dot k or k dot I will be 0. Now consider this product of these two vectors, the scalar product or dot product. Here a bar is I bar ax plus j bar ay plus k bar az, and b bar is I bar bx plus j bar by plus k bar bz. So these two vectors we just take their dot product or scalar product. Now here the first term, how do we do this in general mathematics? We take first single term and then multiply this whole bracket. So take first term, multiply with whole bracket, plus the second term, the whole bracket, third term, then whole bracket. Now multiply the individual terms. By multiplying the individual terms, so we get this like I bar dot I bar ax bx. So this is first term and so on. You can get this. This is very simple. So just see here, this term I bar dot I bar, j bar dot j bar, k bar dot k bar and their components. So we know this identity here, I bar dot I bar, j bar dot j bar, k bar dot k bar are 1. So for them we will write the value 1, and the others like I bar dot j bar, I bar dot k bar, so their value is 0. We know this, we have seen the characteristic of vector scalar product, the fifth one, so that they will be 0. So obviously all these terms will get cancelled and we will get a bar dot b bar is equal to ax bx. So only these 3 terms will remain, so ay by and az bz. If a bar is equal to b bar or b bar is equal to a bar, we can write a bar dot a bar is equal to here it will be ax square plus here ay square plus here az square, or if b bar is equal to a bar, then b bar dot b bar is equal to bx square plus by square plus bz square. So that is the square of their individual rectangular components. Now we know this has a bar, this as a square and this as a b square, or in simple terms it will be a, that is square of the square root of this one, so that is under root ax square plus ay square. We know this magnitude. Okay, so similarly for b it will be under root bx square plus by square plus bz square, that is square of their individual components, and then take a square root. Now let's take an example to understand the scalar product. Okay, we know if consider here is a body, it is displacing through this distance and force is F bar is acting on that body, for it is responsible for this displacement. But in regular cases that will be the direction of force and displacement will be same in regular cases, okay, in general. But here they are not in the same direction. Displacement is occurred in this direction, and the force is applied is along this direction. So in this case we need to consider the component of force along this direction, that is F cos theta. We can see here it is theta, it is force, so that will be the F cos theta, that is component of applied force in the direction of the displacement. So displacement is from this to this, that is in this direction, this place to this place. Okay, so we need to consider vector quantities here. So just consider the total force applied, and that is F bar, but this force applied in the direction, or the responsible force, actual responsible force in the direction of the displacement, that is F, sorry, here that will not be a bar. Okay, we are taking just magnitudes, F cos theta, okay, that is magnitude of force applied in the direction of the displacement into the displacement, so that is S. So we can write it as a F as cos theta. So here we know this is magnitude of F, magnitude of S, and angle between them, so that will be F bar dot S bar, that is a scalar product. So resultant of a scalar product we know is a scalar quantity, that is nothing but a work done. So work done is equal to the force, or the component of a force in the direction of the displacement, and or the responsible component of force in the direction of the displacement, and multiplied by the displacements. It is a product of both these. So work done is a scalar quantity. Using this we can see it is a scalar quantity. Power, so we know it is work per unit time, so that will be work by time t. So work we know from this equation, F bar dot S bar by t, but here S bar by t bar is nothing but a vector quantity, that is velocity. So F bar power will be F bar dot V bar, that is product of force and velocity. Both are vector quantities, but their resultant is a scalar quantity. Now we will see vector product or cross product. Consider a plane or plane of this paper, okay, in which we will take two vectors as a bar and b bar through angle theta. Now if we want to find the a bar cross b bar, okay, we will write a bar ab sine theta. Okay, now AB sine theta is a magnitude of A bar cross B bar, and A bar is a vector along the resultant. Okay, resultant, how to find the resultant of A bar cross B bar? Take the right hand, okay, right hand thumb rule. For this we use right hand thumb rule to show the resultant's direction. Here it is a magnitude of resultant, so A bar is a direction of the resultant. Now I will show you the how to find the resultant's direction. Take the right hand and curl the fingers from A bar to B bar through a smaller angle. Okay, this is a smaller angle theta, not this big one. So from A bar to B bar, just take the smaller angle and curl your fingers. The outstretched thumb, okay, the outstretched thumb that is perpendicular to them is resultant's direction, A bar cross B bar. So A bar is unit vector along this direction. Okay. So vector product's resultant is not a scalar, it is a vector. Okay, because this A bar. Now here vector product is not commutative, that is A bar cross B bar is not equal to B bar cross A bar. That means it changes its direction. Okay, so see this diagram again. Here A bar cross B bar's resultant is this. Now B bar cross A bar's resultant will be opposite, because we have to come from B bar to A bar. We have to curl our fingers, not like this. Now do your hand, change your hand's direction and curl it from B bar to A bar. Okay, through smaller angle. Okay, so like this, and your thumb will stretch to a downward direction, that is opposite to A bar cross B bar. So that will be the B bar cross A bar. So here A bar cross B bar is not equal to B bar cross A bar. So from this we can show it is not commutative. That is first property of this vector product. That is A bar cross B bar is not equal to B bar cross A bar. Its magnitude is given by this AB sin theta, and this magnitude is given by AB sin theta minus. Now here vector product obeys distributive law over vector addition, that is A bar cross B bar plus C bar is equal to A bar cross B bar plus A bar cross C bar. So this vector product obeys distributive law. It does not obey commutative law, okay, but it obeys distributive law like the scalar product. You can verify this. Okay, now if the two vectors are parallel to each other or anti-parallel, their angle will be 0 or 180, we can see. So sin 0 or sin 180 are 0, hence the whole term will get 0 and we will get a resultant 0. So if we are taking a vector product of two vectors which are parallel or anti-parallel, then their product, the vector product, will be 0. Now consider this. If A bar cross A bar is equal to 0, that means a vector product of a vector with respect to itself. Okay, so that will be again 0, because a vector with itself is a parallel one. Similarly, unit vectors, in terms of unit vectors, I bar cross I bar is equal to 0, J bar cross J bar is equal to 0, K bar cross K bar is equal to 0, because they are also parallels to each other. But consider if they are perpendicular, these unit vectors are perpendicular, then we can see here, that is in the x direction, let's take this as a y and this as a z. Then for x the unit vector is I bar, for y it is J bar, and z it is K bar. So if we take the I bar cross J bar, if we take this one, the vector product of I bar cross J bar, the resultant will be, you can see here, if we curl the fingers from I bar to J bar through a smaller angle. Now consider the three axes, the rectangular components, the unit vectors along x, y and z direction, that is I bar, J bar and K bar. Okay, so if you want to find I bar cross J bar, that is I bar to J bar, if I curl the fingers like this, so this will be the resultant, that is a perpendicular to both of these two, that is a K bar along the direction Z axis. So the resultant will be K bar. Now if I want to take the J bar cross I bar, that is opposite to this, so I have to curl the fingers in opposite direction, so that will be the direction, that is negative Z axis. Okay, so that will be minus K bar, so the resultant will be minus K bar. So for all of these axes we can do similarly and write J bar cross K bar is equal to I bar, and K bar cross J bar is equal to minus I bar. Similarly, k bar cross I bar is equal to j bar, but I bar cross k bar is equal to minus j bar. So this is again a characteristic of a vector product. Consider an example with the two vectors I bar, b bar. So just take the vector product or cross product of these two vectors. We write the individual term and the whole brackets multiplication or the vector product here. So first term the whole bracket, second term the whole bracket here, third term cross product with the whole bracket. So writing the individual terms product, okay, so like this we know here I bar cross I bar is 0, okay. Similarly j bar cross j bar, k bar cross k bar also 0. We know this property or characteristics of a vector product. Now I bar cross j bar is nothing but k bar. We know this, okay. Here this is again another property. So I bar cross j bar is k bar. So similarly writing this we can write for I bar cross k bar. For this I bar cross k bar, here it is I bar cross k bar, it is minus j. So minus j bar ax bz. Similarly for all of these terms, so solving similarly for all of these terms we get by and after taking the commons outside I bar j bar and k bar, here the minus is here, okay. So we know expansion, this is the expansion of a determinant, okay. So for this consider this determinant. So this expression is expansion of this determinant. This expression here, this expression is expansion of this determinant, that is a bar cross b bar is nothing but determinant of I bar j bar k bar, and in the second row ax ay az, and third row bx by bz. Now consider these two vectors as a bar and b bar. Now let's make a parallelogram using these two vectors at the adjacent sides of a parallelogram, okay. Now if you want to find the area of this parallelogram, we need this height, okay, this perpendicular from this terminus of b to the a bar, okay. So this is a perpendicular from terminus of b to the a bar, okay. So if you want to find the area of this parallelogram, let's say o c d e, okay. So if we want to find the perpendicular, we need this OE into, let's say this point P, okay, into CP, that is area of parallelogram OCDE. So for this we need this base and this height of this parallelogram, that is OE into CP. But here OE is a bar and CP, we know CP is H. H is what? H is its, let's say H as its height, okay. So we know this theta angle between these two vectors a bar and b bar. So if this is a theta, we can say this H is a b sine theta, okay. Is it right? So H is equal to b sine theta. So just put this value, sorry, b sine theta. So we can see here AB sine theta. So area of this parallelogram OCDE is nothing but AB sine theta, but we know this is A bar cross B bar's magnitude, okay. So magnitude of A bar cross B bar is nothing but a area of parallelogram as these two sides as taken as adjacent sides of that parallelogram, or these two vectors taken as adjacent sides of a parallelogram. In physics we also see torque as a vector quantity. It is a resultant of a vector product of magnetic moment and magnetic field induction. So M is magnetic moment and B is magnetic field induction. So we know another relation, linear velocity, as a result of a cross product or vector product between this angular velocity vector omega bar and the radius vector r bar. So the derivative of a vector with respect to a parameter like velocity or acceleration. Now consider a particle at p, it moves from p to p dash. Particle at p at a time t and particle at p dash at a time t dash. So if we trace the position vectors, that is op at a time t and another one will be op dash, that is at a time t dash. So this op we can represent it as a r bar and op dash as a r bar dash. So these are the positions vector at time t and at time t dash. So these are the two time intervals here, two time instances. So that will be the position of particle. Now with respect to this position, these are the rectangular components of each vector like this: I bar x plus j bar y plus k bar z. Similarly for op dash, r bar dash is equal to I bar x dash plus j bar y dash plus k bar z dash at a time t dash. So we from these two we can calculate the displacement of this particle, that is this distance or displacement, that is a dou r, that is difference between these two positions. So that will be dou r bar is equal to op bar dash minus op bar, that is r bar dash minus r bar. So calculating these two, we will get I bar dou x, that is a difference between this x dash and x, dou y, that is a difference between y dash and y, and dou z, difference between z dash and z. So individual rectangular components, so that difference is in between the individual rectangular components. And here the time difference is t dash minus t, because this position at time t, this is a position at time t dash. Now consider the average velocity of particle. So how do we define the average velocity? There are two types of velocities. One is average and second is instantaneous. Okay, instantaneous, that means at any time t. Average velocity is nothing but, for example, consider a car travels from this point at time t, this t plus del t. Now what happens here? If the car travels from this t to t plus del t, we let's say it travels it in 50 kilometer distance, this distance in 1 hour. Okay, 1 hour. Then we will take this total distance, this total time, so that will be average velocity. Now if we want to find instantaneous velocity at any time, this, let's say t dash, at this time, what is the velocity of that vehicle, then we have to choose this, we have to use different formula, that is not average velocity, that is instantaneous velocity. Now what we do, we just make this interval of time, that is del t, this del t from here to here, this del t very small, nearly equal to 0 but not equal to 0, as we are finding the instantaneous velocity. So we will just narrow the time interval and find out the velocity at this time t dash. This time here or here, we can find it anywhere, that instantaneous velocity at any time t. So that will be the instantaneous velocity. Now what we how we narrow this time interval? We will just take the limit as dou t tends to 0, that means this dou t, del t or dou t, it's tending to 0, that means its value is nearly equal to 0 but not 0. So by this we can get the instantaneous velocity. Now by the definition of derivative, we know this value, that means this term is nothing but a derivative. So instantaneous velocity, we can write it as a derivative of r bar with respect to dt. So in terms of components, we can add write this again, this r bar we can write like this. So again putting the limit, we will get the v bar as v bar vx plus I bar vx plus j bar vy plus k bar vz and its magnitude. So this is a this is derivative of a vector with respect to parameter velocity. The second one is acceleration. You do it on your own, you will get the notes. So do it as a homework.